index of n equals for Young's theorem. Okay, so let me remind you, we had, somebody help me with the formula. We had delta is equal to E minus 2J1 plus minus H1 minus H2 minus H3. Was that correct, please? Somebody? Yes? And we had our, okay. And then we had this table of, we had this table with charges. And here we listed Watt field. And here we listed delta, J1, J2, H1, H2, H3. H1, H2, H3 we took as a unit. And finally, sorry, E. And delta. Okay? We had these, the chiral scalar fields which had energy 1, 0, 0, plus minus 1, 0, 0, 0 plus minus 1, 0, and 0, 0 plus minus 1. Right? And these guys had delta is equal to 0. Right. Then there were the anti-chiral scalars. Bar which 0, 0, 0, and then minus of these. So what am I saying? These were all pluses. Thank you. These were all pluses. And these were minus 1, 0, 0, 0, minus 1, 0, and 0, 0, minus 1. And this guy had delta equals 2. So the important thing is not 0. Then we had the fermions. Okay, so our fermions were in there were fermions that were in the chiral representation of SO6 and the anti-chiral spinor representation of SO6. All fermions, okay, and the guys were alpha 0, and this was anti-chiral under SO6. So chiral under SO, chiral spinor was anti-chiral under SO6. Okay, this guy had dimension 3 halves. This guy had J plus minus half, 0, and then this was anti-chiral, so we got everything is half times plus minus plus minus plus plus or minus minus minus. Okay, all these are plus means plus half, minus means minus half. Okay, and then we checked what delta was. For these guys, I believe we got delta equals 0, right? Because we got 3 by 2, and then, so delta here was equal to 3 by 2, then minus 2j, so minus plus minus half, and then minus 2 plus minus half, and minus those guys there summed up to 1 to 1. So we got minus 1. So if we choose half, thank you, minus half, because they're spinors, yes, thank you. Minus half, and so this guy which was, the guy which was minus 1 will work, and minus 1 came from plus half, and so plus minus chi plus minus plus and chi plus minus plus plus was delta equals 0. On the other hand, if we took the chi minuses of the same guy, okay, this would flip from minus to plus 1. So we have chi minus same is delta equals 2. Okay, and then if we look at this special guy, one more than each of these. So it will be either 3 and, or is it 2 more? It has minus 3 halves. Yeah, this guy will come with a minus, with a plus 3, with a plus 3 halves. So 2 more than each of them. Okay, so that guy will have either delta equals 2 or delta equals 4. So the guy with plus plus minus will have delta equals 2, and the guy with plus 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 will have delta equals 4. Right, so all of the important thing is that this is the only delta equals 0 state. Right, then we looked at the field strength. Okay, and what? Oh, psi 0 was chiral? Oh, I did that wrong? Sorry, let me check. Thank you, psi 0 alpha, yes. Psi 0 alpha, thank you. There was also the guy that was here, and this was chiral. Thank you, I had to check that. Yes, so this was 3 halves. This J1 is equal to 0, J2 is equal to plus minus half. Okay, for this guy, delta is equal to 3 by 2 minus whatever we get. Now here the charges are plus plus plus, plus minus minus, minus plus minus, and minus minus plus. And for plus 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 it was 0. Let us, yes, of course, because 3 by 2 cancels 3 by 2. And for everything else it's some positive number. Right, so thank you. So there was psi 0 alpha plus plus plus. This has delta equals 0. Rest positive. Okay. Then there was f alpha beta. Then there was f alpha beta. And f alpha beta had dimension 2, had energy 2. Now f is spin 1 plus spin minus, spin 1 under SU2 plus spin 1 times spin 0 plus spin 0 times spin 1. Right? So this is sort of 1 0 plus 0 1, by which I mean the whole multiplet. Right? So the charges are 1 0 and minus 1 here, and 1 0 and minus 1 here. Not So I should write here J1 plus J2, because if it's 1 here, it's 0 under J2. And if it's 0 here, it's 1 under J2. So this encompasses both these, J1 and J2. Clear? Okay, then the H's, of course, was 0. And the only way this can become delta equals 0 is if the 2 in the energy cancels 2 in angular momentum. Angular momentum is 2J1. So that can happen if J1 is equal to 1. So F plus plus, F, plus plus, by which I mean spin 1 under the first SU2 and spin 0 under the second. I hope the notation is not confusing. This has delta equals 0. Okay, and then we looked at equations of motion. The only delta equals 0 equation of motion. Okay, first we looked at derivatives. So the derivatives that had charge, remember derivatives had charge plus minus 1, plus minus half, plus minus half. Because a vector is a bispinner under SU2 times SU2. And the guy with, so del plus alpha was delta equals 0. Because its energy was 1 and its angular momentum is half. So E minus 2J1 gives delta equals 0. And these guys have plus minus half under J2. Half under J2, this is plus half here. This was 1 here, this was 0 here. Delta equals 0. Not writing the other derivative, del minus, because it's not delta equals 0. Okay, so these were the delta equals 0 derivatives. Okay, and finally we had equations of motion, and we also should write the supersymmetry. So the equations of motion that were relevant were equations of motion that you could make with only a supersymmetric derivative. Now del square has all indices coupled with epsilon, and epsilon couples a plus in the left SU2 with a minus in the left SU2. So del square is not made only out of supersymmetric derivatives. This is clear? So any equation of motion involving del square was not supersymmetric. Clear? Okay. So something that involved only the supersymmetric derivative, the Fermion equation of motion for this guy. So the fermionic equation alpha dot is equal to 0. But alpha dot involves switching, right? It's coupling with the epsilon. So plus here couples with a minus there if we lower both indices. Okay? And so this is the, anyway, it didn't matter. One thing is that here we could use it with a plus. So we have del plus and then alpha psi alpha, alpha dot psi alpha dot equals 0. Okay, and that equation of motion was supersymmetric. So we'll write that down. So del plus alpha dot psi alpha dot. Okay, now this thing has energy 5/2. Okay, it carries angular momentum half because of the plus here. It has J2 equals 0 because these contract. Okay, it H's. The H's are same as those for this, so that was plus plus plus, always halves. Okay, and now let's check that it's supersymmetric. I 5 half minus 1 minus 3 halves. Okay, and I believe that was the only supersymmetric equation of motion that we had. Okay, so this was a reminder of the space of fields in this theory. Okay. Any questions about this before we continue? Because we acted on the guy which was plus plus plus. These three were not supersymmetric. This guy was supersymmetric. Supersymmetric means delta equals 0. We acted with the equation of motion on that guy, and the derivative doesn't carry h, so it doesn't change its charge. Is this clear? Okay. Any other questions or comments? Please.
There is a comment you made, so f plus plus is self to 1.
F plus. Okay. Let me explain that. See, in general D dimensions, an antisymmetric tensor like f alpha beta is an irreducible representation. If D is greater than 4, f alpha beta is an irreducible representation. Okay? All elements of the antisymmetric tensor can be transformed to each other by rotation. In D equals 4, it's not. How do we know it's not? We know it's not because D equals 4 contains an epsilon tensor. Okay? So, we can take this epsilon tensor and do the following. Epsilon alpha beta mu nu f mu nu to get another antisymmetric tensor out of the original antisymmetric tensor. Okay? Both of these are antisymmetric, so they transform the same way under rotation. So any equation you write for them is covariant under SO4. Okay? So now this operation of taking an antisymmetric tensor and multiplying it by epsilon, getting another tensor has a name, it's called star, the dual. And I should put a 2 factorial there, 1 over 2 factorial. Now, it's easy to convince yourself if you've got the 2 factorials, right? That if you star again, you come back to the same thing. Star squared is equal to 1. Okay? Therefore, one can impose a condition. Therefore, the star operation. The kind of operation, the kind of equation I want to impose is star of f is equal to alpha times f. Because this kind of thing will be covariant under SO4. But because I do it again, this equation will only be consistent if alpha squared is equal to 1. These are real fields, so there are two possibilities, alpha is plus minus 1. Okay? So the two possibilities for such equations to impose, star f is equal to f and star f is equal to minus f. These equations commute with rotations, and so you get irreducible representations only after you impose these equations. So the first guy is called a self-dual field, second guy is called an antisymmetric. Now, this was from the point of view of SO4. How do you see the same thing from the point of view of SU2 times SU2? From the point of view of SU2 times SU2, we can ask what was the antisymmetric tensor F? What kind of representation did it transform in? Okay, so now the antisymmetric tensor, one easy way to figure this out is to remember that the antisymmetric tensor was the adjoint. So the generators of SO4 transformed in this representation. But adjoint is adjoint, so it should be the adjoint representation of SU2 times SU2. But the adjoint representation of the first SU2 transforms in spin 1 and of course spin 0 under the second SU2. While the adjoint of the second SU2 transforms in spin 1 under the second SU2 but a 0 under the first SU2. So clearly the adjoint is 1 0 plus 0 1. And now we see how beautifully these two things come together. The adjoint in this case, because it was a product group, wasn't one representation, one irreducible representation, it was two. And that matches exactly with the fact that if you think of it in terms of SO4, you have an equation you can put. So, of course, now there is a matter of convention, but with one convention, the self-dual tensor is the 1 0, and the anti-self-dual tensor is the minus 1. Okay? Now, we were working with the 1 0, right? Because we wanted plus plus under the first SU2 for supersymmetry. That's why. It's not equal to, but you can impose the condition. Every antisymmetric 2 tensor can be written as the sum of a self-dual antisymmetric 2 tensor and an anti-self-dual antisymmetric 2 tensor. Okay, so we are only looking at the part that is self-dual because that's going to be the part that is supersymmetric. In particular, we're looking at the self-dual part and one of the three possible charges of that. Okay, so as you say, the full representation is not self-dual. The full field content is not. But you see, we're not looking at full field content. Looking at those parts that are supersymmetric. Is this clear? Excellent. Go on. It's important. Delta equals 0 is important because if you remember from last class, what we argued was when we try to compute this trace minus 1 to the f times e to the power mu I hi, only states with delta equals 0 contribute. Any state that has delta not equal to 0 will not contribute. So we are trying to compute the index now. For that reason, we are only concerned about those things that have delta equals 0. I'll make that a little more precise as we go. But because only delta equals 0 states contribute to the index, that's why delta equals 0 is important. Anything that has delta not 0 does not contribute to the index. Now, you may be worried that this sounds extremely naive. What do you mean a letter field has delta equals 0? Haven't we read in quantum field theory that you take an operator made out of many fields and the operator has dimensions which have nothing to do with the dimensions of the original building blocks? That's true in general. But remember, we're talking about an index. An index cannot be continuously renormalized. So we will compute it in the free theory. In the free theory, delta is the sum of deltas. So there's no complication. Isn't it amazing? Okay, great. Okay, so now the next thing I'm going to do is to compute a letter partition function. More precisely, a letter index. Okay. Before I do that, before I do the calculation, let me outline the strategy of the full calculation. What are we going to do? Okay. Maybe before I do that, let me do some kinematics. You see, it's terrible. Okay. Okay. First thing we need to do is to choose a set of charges that under which Q has charge 0. I'm trying to see what choice we made here. Just 1 minute. L1, L2, L3. Okay. Yeah. Okay. We chose the following charges. We chose J2, L1, which is equal to E plus H1 minus H2 minus H3. L2, which is E plus H2 minus H1 minus H3. And L3, which is E plus H3 minus H1 minus H2. Okay, so what am I doing? Remember, our algebra had 6 Cartan charges. Okay? Remember, our index was an index only if we weighted with respect to chemical potentials that coupled to charges such that the charge was evaluated to 0 for Q. Okay? And remember that actually the index is not a function of 5 chemical potentials, but actually 4, because all states carry delta equals 0. Okay? So, I want a basis of charges. I want a basis, the set of charges such that they evaluate to 0 on Q, when evaluated on Q, is a 5-dimensional linear vector space. I want a basis of charges in this 5-dimensional vector space, one of which elements is delta. Remember, we checked the delta, that Q carried delta equals 0. And 4 other elements to span that linear vector space. So this is my choice. So there's, of course, delta, J2, L1, L2, L3. Let's check. I forgot to put here. So we were working with Q plus, 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 and minus half. Okay? And let's check that that works, that carries delta equals 0. What?
Shouldn't that be J1?
No, J2, because we want things that will commute with the charges of. Okay, Q carries a J1 charge, so that will not work. Why this particular choice of L1, L2, L3? Convention. Or we have a 5-dimensional vector space of charges. You want to parameterize it somehow. We just chose some particular parameters. Doesn't matter at all. There's no, we try to be as symmetric as possible. Yeah. It doesn't matter. Doesn't matter at all. See, Q carried this charge, so it had delta equals 0 because half minus twice minus half. So that's 3 halves minus 3 halves. Right? So this had E equals half and J1 equals minus half, J2 equals 0, this was plus, 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 and delta was equal to 0. Okay, so delta was one of the charges that when evaluated on the charges of Q gave 0. Right? Now, J2 is also one of the charges which evaluated on the charge of 2 gives 0, because Q does not carry J2 charge. Simple as that. Okay? And then there were these other three. Look, Q carries half for each of H's and half E. So clearly all these three evaluate to 0, because you had half plus half minus half minus half. So for all three. Can't hear.
Q is like the origin or something.
Origin.
Every value is 0 there.
No. We are looking for those charges which we are looking for those charges such that Q carries charge 0 under those charges. I mean, Q is a fermionic coordinate. It's not one of these things. We're evaluating the charge of Q. So these 5 charges evaluated on Q are 0. Q carries 0 charge for these 5 quantities. Is this clear? So we are allowed to weight with chemical potentials with respect to these charges, and we will get an index. At least an index of states annihilated by Q. Is this clear? Okay. And so now we finally define our index sort of in a clear way here. The thing we're going to try to compute is trace of minus 1 to the power f e to the power minus beta delta minus zeta J2 minus gamma I Li. Oh, plus. Sorry. And minus this. Okay. Now this index looks like a function of 5 charges, 5 chemical potentials. Beta, zeta, whatever that squiggly letter is, I never really know. That thing that looks like an ulta 3, and the 3 gamma i's. Okay? But it's actually not going to be a function of beta, because all states that we evaluate all carry delta equals 0, so it will be independent of beta. However, for a real definition of the index, we need to put that thing, because you see, otherwise you have an infinite number of, it makes it a well regulated problem, because the number of states with any given value of delta is finite. So all cancellations happen clearly once you put this regulator. So you should think of beta as a regulator, which will play no role in an actual computation, but this is the quantity we're computing. Okay, this is how you make sense of all our arguments about states cancelling and so on, because we are dealing with infinities, otherwise it becomes ambiguous. Is this clear?
No, beta is not. Delta is anyway. Here only states with delta equal to 0.
Yes, so why does beta matter at all? Absolutely. It doesn't in the end. The answer will not depend on beta. But you see, all these questions about whether fermions cancel bosons or not.
You're saying in excited states the cancellation is argued through this non-zero.
I'm saying that at any given value of delta, there's a finite number of states. And so this cancellation question is a clear question. If we had beta equal to 0, then we would look at all states together. There's no grading. Then there's an infinite number of states. And whether things cancel or not depend on how you group things. Do you know what I mean? If you take 1 plus 1 plus 1 plus 1 plus minus 1 plus minus 1 plus minus 1 plus minus 1, there's an infinite number of 1s and an infinite number of minus 1s, you can get any integer you want, right? Right, so to avoid having to deal with such silliness, this gives you a regulation of that sum. Okay, so it's term by term, beta by beta. Anyway, as you will see in the actual calculation, it will play a very little role. Just conceptually, this is what it is. So often I will write this trace without the beta. So it doesn't depend on the beta. Okay. Good. Excellent. So now this is the thing we want to compute. So how are we going to compute this in Yang-Mills theory? Okay. So look, we are going to do the calculation in the free theory. It's remarkable because we can do the calculation in the free theory and it will have to be correct for supergravity. We have to be correct at very large lambda and therefore have to be correct for supergravity. So we should be able to check that this thing computed over multi-gravitons is the same as what we get from Yang-Mills theory. Okay, so that's, well, it should work. Okay, but we're going to do the calculation in the free Yang-Mills theory. So let's see, how do we do the calculation? Now, in our theory, first thing we're going to do is use the state operator map. So instead of evaluating states, we're going to evaluate gauge invariant operators. That's exactly the same thing. That's exactly the same thing both formally as well as calculationally. If you took the fields of Yang-Mills theory and put it on an S3, you will find that the set of one particle states on that S3 is simply in one-to-one correspondence with all the operators you can make out of one field. If you just did that decomposition. It's just that we already know the spectrum of operators, so it's a bit easier. Conceptually, we're not gaining anything. Okay? But it's easier to write operators than to write states. So I'm going to do it in terms of operators. Is this clear? Okay. Operators have to be gauge invariant. Why do they have to be gauge invariant? Well, from the point of view of operators, of course, non-gauge invariant operators are not operators. But such arguments are a bit slick. So you might ask, what from the point of view of states? From the point of view of states, it comes from the Gauss law. You see, we've got an S3. And if you try to put a plus charge on an S3, that's impossible because the electric field line's trying to go away and there's nowhere for them to go. All states that you put on S3 have to be electrically neutral in U1 theory. Just because the electric field lines have emerged from something, they have to be as many sources as sinks. Right? Is this clear? So it's just a simple fact of life that states on a compact manifold, in particular, let's stick to S3. There are new issues when you have non-contractible S1s because there are Wilson lines also. We'll ignore that. So let's stick to S3. Just a simple fact of life that you take U1 theory, like QED. Put it on S3, all states have to be charge neutral. This is not true in R3. It's not true in R3 because the electric field lines have somewhere to go, namely to infinity. In fact, this is why we can measure charge sitting at infinity. We just integrate the electric field lines at infinity and say, that's a net charge. In S3, there's no infinity. Just the net charge has to be 0. This is clear? So for a U1 theory, all states have to carry net charge 0. For an SUN theory, you can ask, what is the generalization of the statement? Okay? And the generalization of the statement is simply that all states have to transform as SUN singlets. It's the same Gauss law argument. If you make it a little more carefully, you conclude that all states are SUN singlets. Clearly, right? Because if it was anything but an SUN singlet, you take the U1 factor, it has to have some charge under some U1. You take that U1 factor and you make my argument.
Why are we making this Yang-Mills theory contains on S3?
Why are we making it on an S3? Because that's what we want to compute. We want to compute trace of this quantity on S3. Now you can ask why. Why on S3? Okay, 2 reasons. First, if you try to do it on R3, the problem will be much less well defined because the spectrum of a conformal theory on R3 has a continuum. Okay? So it will be less well defined and less interesting because all you can compute in a theory with a continuum is a density of states. And density of states, dependence on temperature, for instance, is determined by scale invariance, as we discussed in one of our lectures. So the only thing you can compute is one number. Okay? So clearly it's a more interesting problem, also better defined problem, because continuums are always hard to make precise. Whereas discrete states, it's very clear what to count, right? Okay? Yeah. Now, so that's one reason. The second, so clearly it's a much richer object if we compute it on S3, because in the end, if you want, we can take the limit S3 radius goes to 0, to infinity, and you recover your R3 result. It's both easier, it's both better defined as well as richer. It carries more information. Clearly, you can go from S3 to R3, but not the other way around. This is answer number 1. Answer number 2 is precisely because of the state operator map. You see, the spectrum of states on S3 is in one-to-one correspondence with the spectrum of gauge invariance operators of the theory. When I say gauge invariant operators, I don't need to tell you in which space, because gauge invariant local operators are gauge invariant local operators in any space. Now, the spectrum of gauge invariant local operators of the theory is a fundamental property of the theory. For instance, if you're studying the conformal bootstrap, that's like a key input. So if you compute the partition function on S3, you're not merely computing the partition function on some manifold, you're computing the partition function over the basic data of the theory, namely gauge invariant local operators. Okay? So for both these reasons, S3 is very, very useful. Okay? The second reason becomes very clear when you work with conformal invariants. Yeah, I mean, in the old days, people didn't do S3. People did T3. But because we were interested in a conformal invariant theory, it just seemed very natural for us to work on S3. Okay, and that gave us a nice rich object. Is this clear? Okay, fine. Now, so what I want to do is to compute this trace. Now, I'm working in a free theory, so the set of gauge invariant operators are built like this. First, you have trace of something, 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 something. And then you can take trace of something, 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 and so on. Roughly speaking. Okay? Where these somethings are what? They are all the basic adjoint fields of the theory. Now, all the basic adjoint fields of the theory and their derivatives, there's a name for those things, they're called letters. So they're all the letters of the theory. This name was invented by Polyakov. He called these letters and he called traces words. Okay, and I suppose multi-traces are sentences. You don't think he said that. Okay. Okay. So these basic adjoint fields of the theory and all their derivatives are called letters. Okay? Now, crudely at least, what we want to do is to look at all these traces. But why do we need the traces? Just for gauge invariance. So more sophisticatedly what we want is simply this. We want to take the product of all letters. So top, 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 top. This could be any letter, this could be any letter, this could be any letter. And in the end, after taking the product, project onto SUN invariants. This is the Hilbert space of our theory. The Hilbert space of our theory is a Fock space of all these letters. Remember, these letters are n cross n matrices. So it's a Fock space of all these letters. But after taking the Fock space, you want to project on down to the space of SUN invariants. Singlets. Is this clear? So this is the Hilbert space over which we want to compute this trace. Now remember that all letters either at delta equals 0 or delta equals positive. Since we're only interested in those things that have delta equals 0, we just forget about the delta equals positive letters. That's why I listed the delta equals 0 letters so carefully.
So you want to construct from delta equal to 0 set
all the letters. Okay? Now I'm... What?
Otherwise it will increase.
Yeah, you see, because there's nothing with negative delta, you can't compensate. Right? Okay. Now, next question. Is this point clear? That the Hilbert space is the Fock space of letters, remembering they're also SUN adjoints. Okay? Let me call it UN, by the way. Otherwise, I'll have to keep writing -1. Say UN adjoints. Remembering they're UN adjoints, and then in the end, projected down to the space of UN singlets. This clear? Okay.
This trace is doing that thing or
This trace does it, but it's not an efficient way to do it in all phases. Good. Okay. It's not an efficient way to do it in all phases. Why? You see, one way to try to count is to count traces and multi-traces. But this counting gets hard at high enough energies. Why is this? You see, because of this. Consider a 2 cross 2. Consider a 2 cross 2 matrix. M, which is equal to alpha, beta, 0, 0. I mean, if it wasn't diagonal, it would be diagonalized. Okay. Now, consider trace M cube. So, let's consider trace M square, and then trace M cube. Trace M is equal to alpha plus beta. Great. Trace M squared is equal to alpha squared plus beta squared. Also good. Okay, what about trace M cube? That's alpha cube plus beta cube. Okay, but alpha cube plus beta cube, okay, is something that you know if you know both alpha and beta. But by knowing trace M and trace M squared, we know alpha and beta because we got 2 equations for 2 variables. So trace M cube is not independent of trace M and trace M squared. In fact, you can write down a polynomial identity. Trace M cube can be written as some polynomial, so in this case it's easy to do. Alpha cube plus beta cube is equal to A times this thing cube plus B times this into this. Okay, with a little fooling around, you will be able to find the coefficients A and B that make this work. Okay, these are called trace identities. For a single matrix, these trace identities are very easy. And you can, of course, it's a classic theorem of mathematics that all higher traces than if you've got an n-dimensional matrix, then all n plus 1, n plus 2, n plus the trace of m to the power n plus 1, n plus 2, and so on, can all be written as polynomials of the lower traces. This is an old and well easy to prove theorem of mathematics. Okay? Already this makes the point that we want to make, that if we want to count states by counting multi-traces, then we better stop our m, the number of things we put in the n, at trace m, m to the power n, where this is an n cross n matrix. Okay, so you could say fine, that's what we do. We count traces and stop m at trace m to the power n. But this is all good when there's one matrix. When you have 2 matrices or more, trace identities become much more complicated. And there is no known basis. You see, for one matrix, you could find a basis of traces. Trace m squared up to trace m to the power n, such that every gauge invariant was a polynomial in these. For 2 matrices, there's no known basis. In fact, it's believed that doesn't exist a basis in terms of which you can write all gauge invariants. So traces are not a good basis. Okay? Now, if n is large, the first trace identity appears at order energy n. So if you're only worried about states of energies below n, you don't need to worry about this. Then the traces can be treated as independent. This is what happens in the low temperature phase. However, if you go to the high temperature phase where you're dominated by black holes in the bulk, states of dimensions of order n square, traces are a terrible way to think. That's why it's much better to use a more abstract point of view. Just think of the projector down to gauge invariance. Traces are one way of implementing this projection, but it's not a good, it becomes like an overcomplete way at high energies. Is this clear? Okay, excellent.
So more than one matrix is counting argument won't work.
Which counting argument?
Alpha, beta, two independent data for one matrix.
Uh-huh.
So you have
Well, the first thing is that when you have two matrices, you can't simultaneously diagonalize.
but then it's a finite number of elements, right?
It's a finite number of elements. Yes. So the counting argument works. It's true. Good. So the counting argument works. But what is not true is that what was not true is that, you see, I told you can determine alpha and beta. That's true. But the thing that is relevant to us is not just identities, but polynomial identities. Okay? Every time you can write some, what you want is a basis of traces, in terms of which you can write every other gauge invariant as a polynomial, so that you get a Fock space of traces. Okay? So if you allowed arbitrary functions of the traces, you could choose any of the right number. But we want more than that. We want polynomials, because we want to create a Fock space. You know, just the fact that the data is there is not enough. We want to create it as a Fock space of traces. Okay? Excellent. But excellent question, Sunil. Other questions or comments? Okay. Excellent. So now, we're going to take the slightly more abstract point of view. How do we take a bunch of states, Fock space, and then restrict to singlets? We do this by using this remarkable object in group theory called a character. So what is a character? Suppose I have a unitary U n cross n unitary representation U. Okay? And I have this guy implemented in some vector space. Okay, so it's acting on some representation vector space. Then U is some matrix. Okay? Trace U in representation R is sometimes called the character R of U. Okay? Is the definition clear? I have a representation space, I have a group element acting on it, some matrix. Take the trace of that matrix. That's a number. That number depends on two things. It depends A, on the group element, and B, on the representation in which we're working. Okay? That number is called chi R of U. Chi R of U is an extremely useful object in group theory. Okay? Now, why is it so useful? It's useful because this chi R of U satisfies the following two key properties. Chi R1, R2. Suppose I look in the tensor product space of R1 and R2 of U is equal to chi R1 U times chi R2. This is some obvious statement about traces in tensor product spaces. Okay, this is some statement about tensor product spaces, which if you go and check with indices, you will find very easily convince yourself this is true. Okay, this is property number one. This is not so surprising. The second property that is sort of really key, okay, is the orthogonality of traces. Okay, that there exists a measure called the Haar measure, the most round measure, okay, under which characters are orthogonal. Chi R of U times chi star R prime, let's say Rm, Rn, these are irreducible representations now, of U is equal to delta Mn. And for this to be delta Mn rather than number times delta Mn, it implies a particular normalization of these U matrices. Okay, meaning that this a particular normalization of these of the Haar measure, essentially the normalization such that du of 1 is 1. Okay, this is a true statement about all compact groups and more, and I won't try to explain it to you. You can read about it in any good group theory book, which means you can't read about it. Okay. Okay. Fine. Now, why is this useful for what we wanted to do? Why is this useful for what we wanted to do? What we wanted to do is impose the restriction onto singlets. But now suppose I compute I take my product of letters and I compute the character of that product. Then, to impose the restriction onto singlets, all I have to do is take that character and integrate over the Haar measure multiplied by 1, because 1 is the character of the singlet. Whatever I get from that will be the projector onto the space of singlets. Is this clear? One at a time. One of you.
You'll get a number, right, when you integrate the...
I'll get a number, exactly. But, excellent. Was there another question?
I was saying that it's like an orthogonal.
It's like an orthogonality thing. Yes. Kanu's question is an excellent one. And the point is, okay, so let's see. So what are we going to do? What we are going to do is to take the partition function. So suppose we've got these various letters. We will compute the partition function of each letter. We will weight with respect to these charges, and also have the partition function with respect to un, namely compute the un character. So that quantity will carry the information of the chemical potentials. And then when you do this integral, you get a number. But that's what you want, right? Because the partition function is number of states times e to the power minus beta ei. So that number will be the number of states which carry the right charge. This is exactly what you want. All I'm saying is we won't just do this weighting with respect to the chemical potential. We'll also weight with respect to other charges. Okay? If we just weight it with respect to chemical potential, you get the number infinity. But we want to grade that Hilbert space. We want to do more than count the number of states in Hilbert space. Is this clear? What? Well, the character, yes, the character is a group invariant. That is true. It's true that if you take U and do V, U, V inverse, the character doesn't depend on V. So the character depends only on the group element up to rotations within the group, up to adjoint type rotations. Okay? But now what we're going to do is to ask, we're going to use the character as a tool to project onto singlets in the products of representations. Is this clear? Because you see, this is what we have. Our Hilbert space is a product of representations, each representation being an adjoint. We've got many, many different adjoints and we want to project that out to singlets in the product. Is this clear? Because these are multi-particle states, that's why product. It will become clearer as we write formulas. But any other questions? So let's write some formulas. Okay. The first thing we're going to do, okay, is to compute the partition function of each letter, the letter partition function, And remember that it's in the adjoint, so multiply it by the character of the adjoint. Okay, so let me do that calculation. So let me compute the letter partition function first. Okay, let me do it separately for bosons and fermions. For bosons, what do we have? Here we have everything we can build out of phi and its derivatives. Okay, so let's see what charge does phi 1 carry under, well, delta we don't care, J2 is 0. What charge does phi 1 carry under this guy? Somebody? 2, excellent. What charge does phi 2 carry under this guy? Phi 2? No, phi I. There are those are the three charges, 1, 0, 0, 0, 1.
That is 0.
0. So phi 2 and phi 3 carry charge 0 under L1, whereas phi 1 carries charge 2. Okay? And so the boson carries now, did I define my index? I weighted with respect to plus or minus? Plus. Minus. I think there may be a typo here. Anyway, let me pretend that I'm weighting with respect to minus. I'll check. Let's work that our thing is as defined. I may have to flip sides. Okay. So the character phi 1 is e to the power 2 gamma 1. Just phi 1. Just a partition function of phi 1. But there's also phi 2. There's also phi 3. Now, phi 1, phi 2 and phi 3 can be sprinkled with arbitrary derivatives. Okay, these derivatives carry charges under which of these four things? J, what? Delta is not that. L1, L2, L3, correct? Sorry, of all of them. So L1, L2, L3 it carries a fixed charge because it carries charge 1 under L1, L2 and L3 and carries charge 2 plus minus 1 under J2, plus minus half under J2. Is this clear? Let me put a 2 here. Okay, so my derivatives have charge. The first derivative has charge. Okay, so I'm just writing down the answer and then you tell me if you agree. This is 1 minus e to the power zeta plus gamma 1 plus gamma 2 plus gamma 3 into 1 minus e to the power minus zeta plus gamma 1 plus gamma 2 plus gamma 3. This is the full letter partition function of the phis. Do you agree with this? Do you understand it? Del plus alpha is acting on phi, exactly. You can have arbitrary numbers of supersymmetric derivatives acting on phi. When we did this calculation, a similar calculation last time when looking at the conformal group, we subtracted away an equation of motion. But there's no supersymmetric equation of motion. So no subtraction is needed. Is this clear? Okay? So far I've computed the thing coming from phi 1, phi 2, phi 3. Do you agree with this, people? Okay. Now there was one more bosonic letter which was this F alpha beta. That carried charge 2 under energy 2 and so it had plus e to the power nu 1, 2 nu 1 plus 2 nu 2 plus 2 nu 3. It can be sprinkled with derivatives also. So the denominator is right for it also. So if we compute a partition function, this partition function over the set of all bosonic letters, I'm claiming that's the answer. Do you agree with this?
Sorry, why you added that class?
Because of the field strength. Because F alpha beta, it carries J equals
You are writing the bosons.
everything. Is this clear? Siddharth.
Oh, you put it to epsilon.
I put it to epsilon, I'm sorry. I did that so that I didn't have to write by 2. Okay, other questions? Okay, now let me compute the thing for fermions, ignoring this -1. I'll put it right at the end. Because all fermions have -1 to the F is equal to -1. Okay, so fermions. Okay, for fermions, how does it go? What? F has J2 equals 0. The plus plus that I wrote were plus plus in J1. It was J1 is equal to 1, J2 equals 0. That's how F became supersymmetric. Right? So that's why it carried delta equals 0, because E minus 2 J1 was 0, because E was 2. Is this clear? Excellent. Now let me write down the thing for fermions. Okay. For fermions, remember we have 4 kinds of fermions. See, we're always going to get the same derivatives. 1 minus e to the power zeta plus nu1 plus nu2 plus nu3 to 1 minus e to the power minus zeta plus nu1 plus nu2 plus nu3. Because everything is sprinkled by the same derivatives. Okay? Now what should I write for fermions? For fermions I should write, well, first there was the guy with the guy which was psi alpha 0. Psi alpha 0, let's look at its charges. First it carries zeta, this J2 charge 0. Obviously, because it has no J2. Second, let's look at L1. So L1, let's take the guy which was plus, let's say minus plus plus. The guy which was minus plus plus and compute its L1. Okay? So L1 was equal to 3 by 2 plus H1, so that's minus half, minus half minus half, which is equal to 0. But this guy has L2 is equal to 3 by 2. Okay, and now for L2 we wanted plus H2, so that is plus half, minus H1, which is plus half, and then minus H3, which was minus half. Okay, so L2 is equal to 2. And similarly, L3 will be equal to 2. Okay, so do you see that the fermions we will get e to the power 2 nu1 plus 2 nu2 plus e to the power 2 nu1 plus 2 nu3 plus e to the power 2 nu2 plus 2 nu3 for that first set of fermions. All good? Okay? Now, we also have to take into account the last fermion and its equation of motion. Okay, so the last fermion, what were its charges? It's just one guy. It had plus 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 for H1, H2, H3, and it had plus minus half for this angular momentum. So let's look at its L1, L2, L3 charges. So it's 3 halves minus minus half, plus half. So that's 2. 3 halves, minus half, plus half is 1. Right? Plus half, yeah. It's equal to 1. Okay? And so we get plus e to the power, and there were plus zeta plus nu 1 plus nu 2 plus nu 3 plus e to the power minus zeta plus nu 1 plus nu 2 plus nu 3. And then finally, the equation of motion carried no j, and its charge increased, so it carries L1, L2, L3, I believe 2. Can you check that? No, there's no place here.
Yeah, it will be 2 because the dimension is 5 by 2.
Yes. So minus, so this should be up here. I'm sorry for writing it so badly. Minus e to the power 2 nu 1 plus 2 nu 2 plus 2 nu 3. So there are 6 terms up here. 5 with the plus and 1 with the minus. The minus is because it has an equation of motion. You're subtracting away these guys. As we discussed when we were talking about the conformal characters. Is this clear? Okay. So now this is the fermionic partition function over the set of letters. Okay. And we will sometimes be interested in computing, in this problem we will be interested in computing. In this problem we will be interested in computing the index over the space of letters. So that is, let's call this PB and this is PF. So I is equal to PB minus PF. Minus because the fermions carry minus 1 to the F is equal to 1. Equal to minus 1. Is this clear? Clear, Siddharth? Somehow people are looking a bit lost.
I was worried about that last minus thing.
Minus. It's minus because it's an equation of motion. Let me remind you of the logic. You see, we're counting all operators that we can make with this fermion and putting as many supersymmetric derivatives as we want on it. However, operators that are 0 by equation of motion are not new operators in the theory. They're 0. So any operator that was the equation of motion dressed with as many fermions as you want should be removed from this count. Okay? And here, these were the quantum numbers of that equation of motion. Everything can later be dressed with as many derivatives as you want. So everything has the denominator. Go on. But 1 sec. Siddhartha, was that clear?
Yeah. So then I got confused because I thought that term was coming from the last with the minus sign. I thought that was coming from the
Equation of motion.
That is coming from the equation.
These were the two fermions which were antichiral. So the two antichiral fermions could carry plus half or minus half under J2.
Okay, that's where
That's why there were 5. And then there was an equation of motion. Notice that we had 4 bosons. So by supersymmetry we should have 4 fermions. But we had 5 fermions. That's compensated for because we have 1 equation of motion. Kanu. Yes.
How come these fermions are in adjoint?
How come fermions in the adjoint representation? Kanu has been brought up on QCD, where fermions are in fundamental. But in n equals 4 Yang-Mills, all fields are in the adjoint, because all fields are in a single supermultiplet.
But it's something specific
To this theory.
super
To this super Yang-Mills theory. In general in Yang-Mills theory, you can choose your matter fields to be in any representation. It's true QCD usually has them in the fundamental. QCD has them in the fundamental. Okay, and it's true we're sometimes particularly interested in fundamental. But there's nothing wrong with the theory where the matter fields are in the adjoint. Now, if you take n equals 4 super Yang-Mills theory, you don't have a choice. Because all fields are in the same supermultiplet. So they have to transform the same way under gauge and Merrill's. So because the gauge boson did, the fermions do as well. Okay? Excellent. Let's go on. We'll take like 5 minutes extra today. 5 minutes. Okay. Now, there is this issue about fermions and signs. Let me first do the problem with just the bosons. Then I'll add the fermions. Okay? Suppose I had just the bosonic Fock space of all these bosonic letters. And I wanted to compute not the index but the partition function over this. But for some reason I'm doing it only over supersymmetric letters. Of course, the whole thing is only consistent when I add in the fermions. But just as a toy model.
This subtraction
Yes.
is true in the later level, or you have calculated the whole partition function?
I've computed the partition function of letters. This is not of the theory.
Oh, now you'll multiply.
I'll do something. Remember, this is just a partition function over these single particle fields.
With derivatives.
With derivatives, but those are still single particles.
Yes, single fields.
Single fields. Now I have to multi-particle it. Okay? Question.
What is that I
I is the index. We called it IW in our paper. W in honor of Witten. We called it the Witten index.
This is not related to
It is that, because if we computed that thing over letters, bosons would contribute with a 1 and fermions would contribute with a -1 because of the -1 to the power f. So it is that thing. Okay. Great. Now let us proceed. Okay? Let me for a moment ignore the fermions. We'll come back to them. So, what I want to do is the following. The problem I have is this. You see, I have this bosonic letter partition function, but now when I think about it, what I want to do is to weight not just with respect to chemical potentials for these 4 charges, but also the chemical potentials of UN. Chemical potentials of UN, same thing as saying UN character. Okay, so I'm going to multiply this by chi adjoint of U, because every field is in the adjoint. Chi adjoint of U. Okay, so what I'm doing here in this case is computing this times U. Suppose this is not in the exponent. Let me write it. Suppose I was interested in calculating this object. Okay, since each letter is in the adjoint, this problem splits up into product and you get chi adjoint of U. Why I'm interested in calculating that will be clear in a moment. You will see. Is this clear? So I've computed that quantity and I get that with chi adjoint of U. Now I'm faced with the following problem. The problem I'm faced with is I know a single particle partition function. And from that I want to create the multi-particle partition function. Question, how do I do it? This question is as old as, I don't know, Bose or Einstein. Maybe they didn't address it in the language I'm going to address it. Feynman's beautiful book on statistical mechanics addresses it in the language I'm going to address it. Okay, I'm going to give you the answer, then explain where the answer comes from. Okay, there is this general question. If I have a Z single particle of beta for bosons, how do I get the multi-particle partition function? First I'm going to give you the answer, then I will explain it. Okay, Z multi-particle, full Z, is equal to exponential of sum over n z sp of n beta divided by n. N is equal to 1 to infinity. Does this formula look familiar? Have you ever seen it before? Grand canonical.
Instead of n, it usually n factorial or something.
It's true, it takes into account both statistics. But grand canonical, I don't know what you call grand canonical. Maybe it's grand canonical, something over arbitrary particle number. But all I'm doing is computing trace e to the power minus beta h. Okay? But have you ever seen this relationship between the multi-particle partition function and single particle partition before? Yeah, you should have. This should be part of your statistical mechanics courses. It's just not language people like to use, but it's very useful. But of course, if I asked you, if you were in the TIFR admission interview, and I said, here, I have a single particle spectrum which has 5 energies, E1, E2, E3, E4, E5, and compute for me the multi-particle partition function with no restriction on particle number. Okay, immediately all you guys would go and say, well, the way to think is not particle by particle, but state by state. Because each state can be occupied arbitrary numbers of times, and because each state can be occupied arbitrary number of times, if I had energies E1, E2, E3, E4, I would have, for the first guy, I would have 1 minus e to the power minus. Because if you expanded this power series, this geometric progression, you get 1 plus beta E1, that's occupying once, plus 2 beta E1, that's occupying twice, and so on. So if there's no restriction on number of bosons you can put in this single particle state, it would be this times and now if it wasn't 5 states but an arbitrary number of states, you have 1 minus e to the power minus beta and then this product over all states. This is your partition function. So now I write this as exponential of minus sum over I minus log of 1 minus e to the power minus beta ei. Where I is the spectrum of single particle states. All I've done is write, I've taken log and put it in the exponent. Minus because it was 1 over. This is clear? Okay? Next, I take log and I power series expand it. Okay? This becomes exponential of plus sum over I, sum over n, e to the power minus beta ei n by n. Where? What? To the power n, which is multiplying by n. Right? Where I'm using the formula 1 minus x, log of 1 minus x is equal to sum over n minus sum over n, x to the power n by n. If you took log of 1 plus x, there would be these additional minus 1 to the power n plus 1s, and log of 1 minus x has a better expansion. Okay, and that extra minus sign here went in killing this minus sign to make it a plus. Okay, now I interchange the sums. And since we're all physicists, we don't ask why we can do that. We do it, and we get exponential of plus sum over n, sum over I, e to the power minus n beta ei 1 by n. But this is simply z of n times beta. Because it's the sum over all single particle states, but weighted with n times beta. And therefore, that's that formula. So it's nothing, right? It's like 3 lines to go from there, 5 lines to go from one formula to the other. It's not any new physics that you didn't know, but it's a very useful form. Given the single particle partition function, what is the multi-particle partition? If we put in classical StatMech without both statistics or Fermi statistics, the answer is exponentiate. Because the n factorials that come from the exponential take into account the identical nature of particles. But when we do more precise statistics, it's that plus corrections. And those are the terms with n equals 2, 3, 4, 5, 6. Okay? Great. Now, suppose I repeated this thing for fermions. Suppose I repeated this thing for fermions. Okay? When you do this actual calculation for partition function, you will get extra minus signs here, because you will get log of 1 plus, and there will be another extra minus sign because the guy was not in the denominator but was in the numerator. So there will be all kinds of minus signs. Easy to work out, not difficult. But it's actually very beautiful when we do the index. Okay? Because when we do the index, we want to weight fermions, the state with the net fermion number of net occupation number of any given state. Okay? And that has its own minus signs. So I'll leave it as an exercise for you. Just generalize this computation. Now to the computation, let me start I'll write the first line. Actually once I write the first line, it will become clear. For fermions, if we were computing partition function, it would be 1 plus e to the power minus beta e1 into 1 plus e to the power minus beta e2. Right? But we're computing index. So it becomes 1 minus. And now we get the same thing that we got for bosons. So we will have the same kind of expression up there, except that it's in the numerator rather than the denominator. So it'll come with an overall extra minus sign. But the overall extra minus sign is exactly what makes it the letter partition index. Okay? And so we've concluded that the index for multi-particle states I is simply equal to exponential for the sum over n I sp of beta I, whatever, all the chemical potentials, n times beta I, divided by n. So you compute the index over single particle states and use that formula, and you get it. Okay? So now in this index over single particle states, we have what we had for the bosonic index minus the fermionic index, but both of those are dressed because we're weighting. When we compute this index, I include this u inside the trace. So what we will get in our context is this quantity times trace adjoint of u. But if we're doing un, trace of the adjoint of u is simply trace in the fundamental times trace in the anti-fundamental of u. Okay? If we're doing SUN, there's a minus 1, which is a pain to keep. So we get, this is same as trace u dagger. Okay? And where we have this to the n, this goes to the n, this goes to the minus n, let's say. Because u dagger same as u inverse. So the full partition function here will be this ISP n beta I by n times trace u to the n, trace u to the power minus n, divided by n summed. This is the partition function when we trace over the whole Hilbert space of the theory, keeping track not just of the chemical potentials we want to keep track of, but also tracing with respect to u. Is this clear?
The last bit,
This.
formula, how this is related to the trace UN?
It's this. We're computing this quantity
Yes.
over the Hilbert space.
Yes.
So this U is just some other chemical potential. So just like we do n beta, we also do U to the n. Is this clear? And then I use the fact that trace of U in the adjoint is trace U times trace of U inverse.
Why is U in the exponent?
For the same reason that this I was in the exponent. The whole single particle guy, see, what I'm using is this formula, that I multiparticle is equal to exponential of I single particle n times chemical potentials.
Oh, all the chemical potentials will get now n.
Yes, including the chemical potential U. Trace of U to the power n.
Now where this minus n?
Wait, why is it not trace U to the power n? It's because, imagine that U is a diagonal matrix. No, it won't be the same. Even if it's diagonal, one is x to the power n, x1 to the power n plus x2 to the power n. The other one is x1 plus x2 the whole to the power n. No, but which one is correct? You see, imagine that U is a diagonal matrix. Then our various states, what we're doing is weighting with respect to the chemical potential, and the eigenvalues are e to the power alpha I alpha 1, e to the power I alpha n. Then what are the chemical potentials? The chemical potentials are with respect to these cartons, H1, H2, H3, H4. And the chemical potential is I alpha. So it's this alpha that should go to the power n, which is what you get by taking trace U to the power n. Okay? So you just think this through. Simple thing. If you compute that quantity, this is what you get. Clear? Diksha is looking puzzled. Yes, there was trace of adjoint of U, but for UN, adjoint is same as fundamental times anti-fundamental. Okay? Okay. If we were doing SUN, this would be trace U times trace U inverse minus 1. Because in SUN, adjoint is fundamental times anti-fundamental fundamental times anti-fundamental gives adjoint plus singlet. So you have to subtract away the singlet part. We're soon going to be doing large n, so we won't even care about those ones. But it's true that if you wanted an exact formula, if we were doing SUN, you would include that 1. Okay? The right formula is whatever it is for trace in adjoint. Here what I've done is write trace in adjoint in terms of products of traces in fundamental and anti-fundamental. Some simple manner. Okay? Now I take this quantity. So far that's this, but I didn't really want this. I wanted the answer without this U. I just wanted the project onto singlets. But now that's cool, because I just take this, integrate du, and that's my answer. Because that projects down to the Hilbert space of singlets. Done. Is it clear? We didn't want to count all states. We only wanted to count singlets. So the only reason I kept track of U.
Sorry, you had to integrate over the hardness.
Yes, this means integral over hardness. The symbol means this.
Use of the elements.
Is this clear? See, it's a simple, beautiful formula, exact formula for the index of n equals 4 Yang-Mills theory. You compute the letter single particle partition function, which we've done on the board. You plug that into the exponent, do this, and compute this integral. Now it's another matter whether you can compute the integral. But clearly you'll agree it's progress, right? Because we take a complicated partition function in a quantum field theory and we reduce it to an integral over one single unitary matrix. Quite amazing, isn't it? As a matter of fact, at large n one can compute the integral over U analytically. And as a matter of fact, we said something wrong about that in our paper, which has been corrected over the last 3 or 4 years. I mean, we didn't say anything wrong about the mathematics. We computed it and we found that when we did this computation for real chemical potentials, we only got one phase. We got a low temperature phase and no black hole-like phase. We used that to conclude that the black holes don't show up in the index, that the cancellation of states between bosons and fermions is so great that in the black holes which we know exist in n equals 4 angles, the index evaluates to 0. So if you want to count their density of states, the number of states, you'll have to do a supersymmetric partition function calculation, more sophisticated than the index. And we were very disappointed by this. So then we did we fooled around in other ways to get other results with using this index, but our main goal was to compute the black hole entropy, it didn't work. And we used this to conclude that actually what is happening is that the index didn't have information about the large density of states of black holes of n equals 4 angles. It's very disappointing. This was 2006, I think. Okay. Now, about 2 or 3 years ago, Seok Kim, Benini, Samir Murthy, and linear combinations thereof, basically pointed out that we'd been idiots. Because they pointed out that one can do this calculation not necessarily for real chemical potentials, which is what we did, because somehow at least I was motivated by thermodynamics. Thermodynamics, we use real chemical potentials. Right? Didn't occur to me we should do something else. But we could do it for complex chemical potentials. And they pointed out that when you do that, you find a phase transition to a new phase. So they pointed out that what was happening was not that the index of n equals 4 angles theory was small, meaning that the number of states, if you compute the index at some fixed, in these chains that I talked about, the numbers in those chains were large. What was happening was that one chain and a neighboring chain were cancelling each other in the approximations we used to calculate this at large n for real chemical potentials. But you could remove that cancellation by going to complex chemical potentials. And once you have that idea, then it's a simple matter to get the actual answer. This answer, when you compute it properly, reproduces, as far as we can tell, black hole entropy. So it's an amazing thing. It reproduces gravitons at low energies and reproduces the Hawking-Bekenstein entropy formula for black holes in the high temperature phase. It's an amazing object. It's an amazing object that we invented for the purpose of computing black hole entropy, and we did that wrong. So it goes. Okay. We concluded it wasn't good enough for that, undervaluing our own invention. It actually was. We were just not smart enough to realize it. Okay, I think we'll stop here.